So now we need to talk about potential energy. You know that potential energy is energy stored due to an object's position. So it's very closely related to work. Work is the way we change energy. So if we want to store energy, we have to get that energy from somewhere. Somebody does work. So work done by a force is equal to the negative change in potential energy of that force. We didn't talk specifically about that negative sign last year, but it ends up being really important. So we'll use gravity to illustrate this. You know, for gravity, if we lift an object up, it gains potential energy. But gravity is doing negative work at the same time, because work is Fd cosine theta. As you lift an object up, you're applying a force, gravity is applying a force, mg. You move it through some height, but the displacement is up and the force of gravity is down. Those are opposite directions. This is cosine 180. So the work done, cosine 180 is -1, negative mgh. But you know the potential energy function is just mgh. So the energy we have stored is because we did work against gravity. Gravity itself did a negative amount of work. So if you know the force through which you're going to store the potential energy, then you've got to introduce this negative sign. So to derive this from the beginning, we're going to do this for a spring. The force exerted by a spring is opposite in direction from the displacement of that spring. So if the spring has been displaced by some other force, some distance x, the spring exerts a force back the other way. So how much potential energy is stored in the spring? So the change in potential energy is the negative work done. You know work is the integral of f dx. So we need to integrate, negative kx dx. So this negative sign comes from the definition. Work done by a force and the potential energy associated with that force are opposite signs. So that's where the outside one comes from. The spring force is in the opposite direction of the displacement of the spring. So that's where this negative sign comes from. So of course the two negatives cancel out. We have positive integral of kx dx. So then we integrate. We keep k. X has an implied 1 here, so that's 2. We divide by the new exponent. We're not going to do plus c here because we're doing a change in potential energy. Really, this is also a change in potential energy. So change in potential energy from the spring. We didn't usually write it this way last year. We wrote US equals 1/2 kx squared. So you already knew this equation, but now you see how it comes from the force equation. So that's how you get to potential energy from a force. But what if you know the potential energy and when you want to get back to the force? Well, we can reverse this definition. If the change in potential energy is the negative work done, so the negative integral of force. So in words, potential energy is the negative integral of force. So force is the negative derivative of the potential energy function. So if we use the u function here, f is negative derivative with respect to position of 1/2 kx squared. Oops, I forgot the k. So we keep the negative sign, and then we take the derivative. Wow, that looks bad. Life goes on. So we keep the 1/2, we keep the k, keep the x, but we multiply by 2. So 2 and 1/2 cancel. We get back that force is negative kx, as we expect for a spring. So next page. We have already defined the word equilibrium. Equilibrium is where the net force equals 0. Now when we're dealing with all of these potential energy functions, we're dealing with a single force. So there are 3 kinds of equilibrium. With a stable equilibrium, this is like being at the bottom of a valley, If you make small displacements, the thing's going to go back to where it was. An unstable equilibrium is like the top of the hill. You can balance there. If the tiniest wind blows, you're going away. And then there's a neutral equilibrium that looks like a flat area. So if I just make up a potential energy function, like that. I have a hill, so that's unstable. I have a valley, so that's stable. And then I have this flat part, so that's neutral. Well, we just said on the previous page that the force is equal to the negative derivative of the potential function. You know that derivative means slope. So the force from a potential versus position graph, force is negative slope of a U-graph. And if we want equilibrium, that's where the force is 0. That's how I knew where these points were. Here we have a positive slope, 0 slope, negative slope, 0 slope, positive slope, and then a long 0 slope. Unstable point because it's the top of the hill, stable point because it's the bottom of a valley, and then neutral because a small displacement, it couldn't really go anywhere. So the rest of the video is going to be a discussion of a particular potential energy function. So here's one that I made up. It took a surprisingly annoying amount of time. That the potential energy function is given by negative 2x cubed plus 6x squared plus 18x plus 8. So before we start, I want to graph this. This is a cubic. So if you remember, the parent function of a cubic looks like this. So this is a negative cubic, so its graph is going to look like this. So you can see that we have 2 points of inflections. We have 2 stability points, and that's part of our job to figure out what they are. So the first thing we're going to do is figure out what the force function is. So the force function is the negative derivative. So when I do this, I like to keep that negative sign on the outside and then just do regular derivative of this whole thing. So the derivative of negative 2x cubed is negative 6x squared. The derivative of 6x squared is positive 12x. The derivative of 18, sorry, there's an x there. The derivative of 18x is 18, and the derivative of 8 is 0. So I'm done there. And then I want to distribute this negative sign. So my force function is positive x squared minus 12x minus 18. So first question, what is the force at the origin? So I just want to evaluate this. F of 0 equals 6 at 0 squared minus 12 at 0 minus 18. So I get an answer of negative 18. So that means the force is 18 newtons in magnitude. The negative sign means it's to the left. It's in the negative x direction. As opposed to, if I do the force at x equals 4 meters, so I need to do 6 times 4 squared minus 12 times 4 minus 18. Plug that all in, you get positive 30. So this force is 30 newtons back to the right. So let's go back to our little graph here. I happen to pick these. I know I don't have a grid on here, but 0 is right in the middle. The slope of that graph is positive. The negative slope is negative. It pushes it back to the left. 4 is over here. The slope of that graph is negative. The opposite of the negative, the opposite slope, is positive. So on that side, it will continue moving to the right. Where are our equilibrium points? Well, the equilibrium points happen when the net force is equal to 0. So I need to take my force function here and set it equal to 0 and solve it. So my force function is 6x squared minus 12x minus 18 is equal to 0. This is a quadratic. It is not an easy one to solve because of that linear term inside. But please notice that all of these are multiples of 6. So I'm going to divide this whole equation by 6, and I get x squared minus 2x minus 3 equals 0, because 0 divided by 6 is 0, of course. Now again, it took me a while to come up with this function because I wanted to make it easy. This is factorable. In general, if you didn't know, you'd use the quadratic formula. But this is factorable. So this is x and x, and this has to be 3 and 1, because those are the only options. We need a negative 2 in here, so this is negative 3 and positive 1. If you don't remember how to factor, shame on you. You can check it. X squared minus 3x plus 1x is minus 2x, and then minus 3. So this is correct. So this means I have 2 equilibrium points. One is located, if x plus 1 is 0, then that's located at x equals negative 1 meters. And if x minus 3 is 0, then x equals positive 3 meters. So again, if I go back up to this graph here, this 0 is at x equals negative 1 meter. And this one is at positive 3 meters. I will ask you to figure out if it is stable or unstable. One way to do that is to figure out, is this a local high or a local low? So I am going to plug in, I need one more page for this. I am wanting to test x equals 3 meters. So I'm going to do 3 points. I'm going to do u of 2.99, u of 3, and u of 3.01. And I better write my u function back over here. Negative 2x cubed plus 6x squared plus 18x plus 8. So, oh, this is going to be annoying. I'm just doing it directly in the calculator. Let me find the calculator. So clear negative 2 times 2.99 to the third power plus 6 times 2.99 squared plus 18 times 2.99 plus 8. I get 61.998802. Then I'm going to do it boring old 3. Negative 2 times 3 to the third power plus 6 times 3 squared plus 18 times 3 plus 8. I get 62 exactly. And if I do 3.01, I get negative 2 times 3.01 to the third power plus 6 times 3.01 to the second power, or squared, plus 18 times 3.01 plus 8. And I get 61.998798. So 3 is, of course, right between 2.99 and 3.01. And 62 is bigger than 61.9988 and bigger than 61.99879. So 3 is at the top of the valley, or excuse me, top of the hill, because this is where u of 3 is located. If you do the same thing with the root at negative 1, or the equilibrium point at negative 1, excuse me, it's not a root of this. At the equilibrium point at negative 1, you're going to find that negative 1 is lower than at negative 0.99 or negative 1.01. You don't have to go quite this way. You probably could get away with doing 2.9 and 3.1, but you can see that this is a local high. Now, for those of you in calculus, I think you're getting close to doing this, so I want to remind you of the concavity test. If you're not in calculus, turn off the video. So the concavity test, that if you start with a function, the second derivative of that function tells you whether it's concave up or concave down. So for this function, we do the first derivative, and this is the regular derivative. We're not doing the force function, which is the negative derivative. So the regular derivative of this is negative 6x squared plus 12x plus 18. The second derivative is negative 12x plus 12. So if I plug in my numbers, if I do this at x equals 3 meters, this is negative 12 times 3 plus 12, negative 36 plus 12 is negative 24. No, the second derivative of u at 3 is negative 24. This means it's concave down because I got a negative, and that's what we showed here. The highest is at u equals 3. If you evaluated at negative 1, -1, you're going to get positive 12 plus 12, you get positive 24, so it's concave up. But again, if you're not in calculus, ignore the concavity test. You don't know it yet, or the second derivative test, however it's called. So potential energy functions, I'll tell you the problem set is going to be on paper because of writing functions and doing graphs. So see you tomorrow.